All right, break is over. So just a reminder, we're in chapter 41. We're looking at nuclear physics. I hope this is interesting. A lot of times, you know, in chemistry classes or whatever, you don't get to look at the nucleus in quite as much detail, and here we do. Here we get to actually derive some formulas, carry out some real calculations, and how fast are the particles coming out of these nuclear decays, how much energy do they carry with them. So we're actually able to get a lot of numerical results. We just got through looking at alpha decays. Now apparently there are what are called beta decays, so let's move on and take a look at those. So this was alpha decay. That was an example. That was a good thorough example for alpha decays. So beta decay. Beta decay occurs when a nucleus emits an electron. Now that doesn't seem to make much sense. Here's an example of a beta decay process. Carbon-14 is radioactive. You may have heard of it. And carbon-14 undergoes a radioactive decay process, but it's not alpha decay, it's beta decay. So what's the difference? Now, I have a few issues with the notation that gets used by the textbook. I think in some places it's a little misleading, I'm going to say. So I'm going to add to this. Anyway, this is the reaction that they've given us. They said the carbon-14 decays by beta decay, and what we're left with is nitrogen-14. Now how did that happen? Carbon-6 only had 6 protons, and apparently a proton, an additional proton, has somehow been created. We got to find out how that happened. And then in addition, there's an electron here. Where did that come from? Is that one of the original electrons from the carbon? And then a particle that we've hinted at a few times, several times, maybe during the semester, that we're finally going to get a closer look at, and those are neutrinos. So let's take a look and see what beta decay involves. Now this is, okay, it is beta decay. So they're going to say that in beta decay, which is accurate, in beta decay, one of the neutrons converts into a proton. We've been talking about how neutrons and protons are, in some ways, they're very closely related particles. Well, now what we're finding out is that there are reactions which involve the weak nuclear force, this additional force in nature. Through the weak force, a neutron can turn into a proton. Or a proton can turn into a neutron, we're going to find out. So there's this ability for protons and neutrons to turn into each other. And let's see how this is. Here's the carbon-14 example. Let's go ahead and take a look. So I'm going to designate this as beta minus. Now, in some future examples that we're going to look at just in a minute here, we're going to look at beta minus, beta plus, and beta neutral. There are 3 variations of beta decays, and we'll see how they're all related. In beta minus decay, a neutron, this is the underlying reaction, a neutron turns into a proton. Now at the same time that a neutron can't just turn into a proton by itself, there's got to be a coupled reaction. And so, I don't know if you guys have heard of Feynman diagrams. If you've watched The Big Bang Theory, they always have Feynman diagrams drawn on the blackboards in the background. Anyway, through the weak force, a neutron can turn into a proton, and at the same time, that reaction is coupled to the formation of another particle antiparticle. The particle that gets formed is the electron, and the antiparticle is the neutral version of the electron, which is called the neutrino. So the neutrino is kind of like the neutral version of the electron, the same way the neutron is the neutral version of the proton. So the electron and neutrino are related in an analogous fashion to the proton and the neutron. So that's what's going on at the fundamental level in this reaction. So what we do with beta decay is this. We write down whatever's going to undergo beta minus decay, and I got an arrow here. And then what I'm going to do underneath is I'm going to write down the underlying reaction. What's really going on in the nucleus? And what's really going on is one of the neutrons turns into a proton, and the proton stays there. So what does that do to the nucleus? Well, the mass number is not changed. You know, if I started with 14 protons and neutrons, I'm still going to have 14 protons and neutrons, but one of the neutrons has turned into a proton. So instead of having 6 protons and 8 neutrons, I have 7 protons and 7 neutrons. Now you might think, well, does the mass go up? Does the mass go down? Does the mass stay the same? In any kind of a radioactive decay, the mass goes down a little bit. The mass has to go down. That's what provides the kinetic energy for the decay to take place. So what it's telling us is that the 14 isotope of nitrogen is going to have less mass, just a little bit, than the 14 isotope of carbon. And so a configuration of 7 protons and 7 neutrons is actually a little more stable than 6 protons and 8 neutrons, and that's why these beta-minus decays occur. It's not necessarily that carbon-14 is unstable, that terribly unstable. It's just that there's something even more stable that it can easily turn into. So yes, this is radioactive, and that's because it can turn into something that's even more stable. Now once you get to nitrogen-14, there's no easy path for nitrogen-14 to turn into something that's more stable, and so it is a stable isotope. Okay. All right, let's see how we would calculate Q values for this. Now looking at the reaction, what I can see is I'm starting off with the mass of the carbon-14. So I got to look that up, and remember, we're going to look that up in Appendix F, and I'm going to have to specifically look for the 14 isotope. So it's 14.0032410 atomic mass units. Now what came out was a nitrogen-14, so I'm going to write that one down. But now I've got to be a little careful with the electrons and the neutrinos, and I even have to be a little bit careful with the nitrogen-14. And here's why. Notice that we had 6 electrons, spectator electrons. They're not involved in the reaction. I have 6 spectator electrons as part of the carbon, and now I have those 6 spectator electrons are part of nitrogen. But 6 electrons is not enough to make nitrogen neutral. And so the nitrogen now is going to be effectively missing an electron. So I've got to remind myself that this is not neutral nitrogen-14, but rather a nitrogen-14 ion, a positively charged ion of nitrogen-14, so it's nitrogen with a plus sign. So I've got to take that into account. I'm missing an electron here. Now at the same time, 2 new particles were formed. This electron is not one of the electrons that was in carbon. It came from this reaction right here. This weak, it's called the weak force that provides this reaction. This is due to a reaction where the neutron turned into a proton and then a particle-antiparticle were formed. So I can't produce one of these particles by itself. That's one of the rules that nature has. At the fundamental particle level, you end up producing a particle-antiparticle pair, and so we produce an electron that balances the charge. This is a plus charge, this is a minus charge, and that means this is an antineutrino, okay, that ends up being formed. It's an antiparticle. So I've got to include the neutrino. Now the neutrino's masses are really, really low. The neutrino masses are like 1 eV. And so we pretty much get used to just ignoring neutrino masses. We just kind of ignore them and treat them as if they're almost 0. But I do have to take into account the mass of this electron. Now, conveniently, the mass of this electron is just what we need to add to the mass of this nitrogen that's missing an electron. If I combine the masses of these two, that will be the same thing as the mass of a neutral nitrogen. So here are the particles coming out of the reaction. I combine these two together, and now that's the mass of a neutral nitrogen. So the mass of the electron I don't need to include because it's going to get included by the nitrogen mass. And the neutrino's mass I can ignore because it's so small. And so all I have to do in beta minus, we'll see beta plus is different, but in beta minus decay, I can take the mass of the carbon-14, the mass of a neutral carbon nitrogen-14, that's my missing mass. That gets multiplied by my energy mass conversion, and that's not very energetic. Carbon-14 decay, the energy release is only 0.1556 MeV. That's pretty low compared with the other ones that we've looked at. Okay? All right. That's how it works. Now, this is just telling us, you know, we've got these new particles, these neutrinos or these antineutrinos. These were predicted to exist. When people looked at these beta decays, they realized that there was something missing. They could not account for all the energy or all the momentum. It didn't match up. There was some kind of a particle that was being missed. It took over 20 years to, first of all, identify reliably neutrinos. Neutrinos are very difficult to detect. Let's see. There is also what is called beta minus decay. Now, beta minus decay, here's an example of neon turning into fluorine, and they're not showing the details. We're going to come back and look at these and show what this means. And then this is what's called beta neutral. I'm going to switch back and forth. They've got the reactions written here, but we need to see a little more detail. So I'm going to take that neon reaction that they just showed us. This is an example of beta plus decay. In beta plus decay, it's a proton turning into a neutron. So the Feynman diagram for this would be a proton turning into a neutron, and the weak force then takes the energy that's been released, the charge, and carries that over and creates a particle-antiparticle pair. And again, the only particle-antiparticle pair that it can create is the electron and a neutrino. This time the electron's going to have a plus charge because, well, the neutrino is going to be neutral, and the electron has to have the charge that was transferred away from the proton. So this is what's called an anti-electron, or a positron. Has the very same properties as an electron. It's got the same mass. It's got a charge of 1, but it's positive instead of negative. So the underlying reaction here then becomes proton turns into neutron with the coupled formation of an anti-electron and a neutrino. And in my diagrams, I write that as the high energy particles coming out. Now this time, notice that the fluorine is going to end up with one more electron than it would have in order to be neutral. The neon has 10 electrons. They're all spectators. They are not involved in this reaction. And so 10 electrons on the fluorine is one too many. So I got to put a minus sign there to remind myself that this is charge balanced. And that's one of the things, for some reason, physics textbooks I feel like don't do a good job of showing the charge balancing that has to take place here. So in any case, what we can do then is, same as before, for the Q value, let's start with the neon. That's what we started with. That's what underwent the decay. I'm going to start with the mass of the neon and then subtract off the fluorine. But wait a minute, that's got an extra electron. And then there's an electron or a positron that's produced, but that's going to be the same mass as an E plus or E minus is going to be the same mass. And then there's the mass of the neutrino. Now, same as before, the neutrino masses, the antineutrino masses, are so small, we can ignore those pretty much in these calculations. But I do have to include the mass of that electron. That is a significant amount of mass. And so what I'm going to do is say that the mass of the fluorine with the extra electron attached is equivalent to a neutral fluorine plus the mass of an electron. So I'm going to take that mass of an electron and add to the existing one. That's going to give me 2 electron masses. Now if we think back to beta minus decay, the electron masses canceled, but this time they don't cancel, they actually double up. And so to calculate the Q value, I go to Appendix F, that's my friend, and in Appendix F I look up the 19 isotope of neon, which is the masses here. I look up the 19 isotope mass for fluorine, which is right here. And then I've got to subtract that off, and I've got to subtract off 2 electron masses. Okay, if I don't get the electron counting correct, my answers are going to be off significantly. So when I did this, I got the missing mass. This is my Q value. I'm going to multiply this by 931.5. There it is. That's the total amount of energy that's going to be released in this reaction. It's going to release 2.217 MeV. If I don't count my electrons correctly, that could throw the numbers off significantly. So I absolutely have to get the electron count correct. Okay, here is a third type of beta decay. Now this is referred to, officially, it's called electron capture. But a few years ago we had a student that suggested, well, why don't we call this beta neutral? And I like that. So, but that's just something that we've used in the course here. It's calling this beta neutral. So the official name again is electron capture. Here's what happens. So let's take beryllium. I think this is the reaction they give us. Okay, so notice the reactions we're looking at are the ones they talked about briefly right here, but they didn't go into a lot of detail. So I'm looking at that lower reaction. Now notice in all of these, we're getting these neutrinos coming out. In this electron capture process, again, just like beta plus, a proton is turned into a neutron. But this time, instead of creating an electron in the reaction, one of the electrons from the beryllium, so one of the electrons from the beryllium itself is converted into a neutrino when this reaction happens. So here's the proton turning into the neutron, same thing we saw before, but this time the coupled reaction is to take one of the electrons from the beryllium and convert it into a neutrino. So that says, oh, in this reaction, you know, the beryllium has 4 electrons that it's bringing along with it. They're not all spectators. 3 of them will remain spectators, but one of those electrons turns into a neutrino. Okay, so one of the electrons goes away. And that says that when we form the lithium, we only have 3 electrons left. Oh, that's all that lithium needs. So lithium is not going to be positively or negatively charged. It's going to be neutral. It's going to have the right number of electrons. Because we got rid of one of the electrons at the same time we got rid of one of the protons. In their places, we now have a neutron that is inside the lithium, but the neutrino is not going to attach to anything. So the high energy particle coming out in this reaction is just a neutrino. And neutrinos, they just travel through everything. They are very difficult to detect because they don't react. And so neutrinos are actually safe. We're exposed to neutrinos all the time. The entire universe is flooded with neutrinos left over from the early high density, high temperature plasma state known as the Big Bang. There's all kinds of neutrinos left over from billions of years ago that flood the universe, and they have next to zero effect on us. So they're fine. So let's see what we're going to do in terms of Q. So for Q this time, I'm going to take the mass of the beryllium, because that's what we start with. And when I look over here, I realize, oh, it's a mass of a neutral lithium. And then there's the mass of the neutrino, and I'm just going to ignore the mass on the neutrino. Say the neutrino mass is so small, not going to worry about that. And so what I can do then is just take the mass of the beryllium, subtract the mass of the lithium, and we're done. And the difference in these numbers, 0.000926 atomic mass units times 931.5 leaves us with 0.8626. Now you can see, if we had rounded back to here, we would get 0 for an answer. So we really do have to keep, typically we have to keep 6 digits. 6 digits past the decimal is what it's going to take to get reliable answers. We want the answers to be in 3 or 4 significant figures. Well, then we got to keep 6 digits past the decimal on these masses. Okay, and I got to look them up in Appendix F. I got to look up the mass of specifically beryllium-7 and look up the mass of lithium-7. Okay, that's the energy that's released in this beta-neutral decay. So interesting, 3 types of beta decay. All of them involve neutrons turning into protons or protons turning into neutrons. All of them involve reactions with electrons and neutrinos. Okay, now this is the notation that the book uses, and this is what makes me a little nervous. This to me looks like an electron was added. And let me go back and, let's go back to here. I think that's very misleading. I'm going to really encourage you guys not to write the reactions this way. The electron that turns into the neutrino is already part of the beryllium. So we need something that shows that. And, the way that I've done that is to write those underlying reactions. But I would suggest using, different, something like this, where you can show exactly what the reactions are. This one's beta plus, and then here is the electron capture. Something that shows that an electron that was part of the beryllium is what's turning into the neutrino. It's not another electron coming out from somewhere. Okay, and then gamma decay. So we did alpha, which was pretty interesting. We did a bunch of calculations there. And then beta, gosh, there were 3 different ways, 3 different versions of beta decay that we took a look at. And now for gamma decay, what happens is if we have an alpha decay or a beta decay, for example, often, immediately after that decay has happened, the remaining nucleus is not in its ground state. What would that even mean? Well, we talked about the protons, there's a set of energy states, the neutrons have a set of energy states. One of the protons or neutrons is stuck in an excited state. So, for example, they're saying when beryllium-12 undergoes beta minus decay, it could decay directly to the ground state of carbon-12, or what also happens, and it doesn't say the frequencies on these, but one of the other occurrences is to actually decay into an excited state. So one of the protons or neutrons is stuck in an excited state, and it takes a little time for that to undergo a second decay, and the second decay doesn't change the number of protons, doesn't change the number of neutrons, doesn't, all the neutrons and protons stay within the carbon-12, but they drop into the ground state, and that releases a high-energy photon. So we've seen plenty of examples of excited states of electrons, or excited states of rotation, excited states of vibration in molecules, where photons get generated. Gamma decay is kind of the same thing. Okay, so again, the textbook has this notation, and if that makes sense to you, that's fine. I actually work better by just writing down some examples. But yeah, so we can start with whatever. If it undergoes alpha decay, Z is reduced by 2, A is reduced by 4, and we have a helium-4 nucleus produced. Beta minus decay, beta plus decay, beta neutral decay, and then finally gamma decay. That's not so bad. I guess I shouldn't be so harsh here on the notation. The one that worries me the most is this one, because to me that tends to cause the most confusion. But all right, let's run some numbers on rates of decay. Some isotopes, some radioactive isotopes decay really fast. They have very short half-lives, and others have really long half-lives. Some survive for a long, long time before they undergo decay, and some of them decay very rapidly. So let's see what it's showing here. Oh, there's the legend. I'm going to go right to the legend. So the legend here says that we started out with a sample of carbon-14 nuclei, atoms, and they're decaying into nitrogen-14. So we start out, everything's carbon-14, and then after a certain amount of time, one of these decayed, and then after more time, another one decays. They're just showing, now they're calling this a random process. That's not quite true. It's true in the sense that the decay of one of these is not influenced by the decay of the other. So maybe a better way to state this is to say that it's an independent process. So each individual nucleus has its own timer. And it's not a fixed timer. It's not there's a fixed time at which it will decay, but there's a certain probability clock that's running. And at a certain instant in time, based on probabilities, there's an ever increasing chance that it will undergo a decay. Let me take that statement back too. So this is where the random comes in also. Let's just look at the math, and then we'll talk about it from there. What it says is that if I have n radioactive nuclei, so I have some number of radioactive nuclei n, then the rate at which that is undergoing decay, the rate at which n is decreasing, dn, is equal to minus some constant times the number times the time interval. Now what that's saying is that the number of decays that we have depends on which isotope of which element, because each isotope of each element has a different decay rate. So this is, let me get the names here. Okay, so we're going to call this the decay constant. So the lambda is a decay constant, and that's something that we're going to work with depending on which isotope we're looking at. Let's see what this leads to. What it leads to is this. It says that there's a rate of decay that's happening. dN dt represents the rate at which particles are decaying. So we're going to put a minus sign in there to show that it's decreasing with time. And this is just a constant, so the lambda is a decay constant. Now, this equation, if we carry through and integrate it, it leads to this. So if you're familiar with following the steps on this, that is great. It's a good chance to go back and think about what you learned in your calculus class. The most important thing, though, is that you're able to use that equation in that we've boxed. So what that tells us is that the number we have over a certain amount of time is going to be, it's going to drop off exponentially. It's going to be equal to the number that we started with minus this exponential drop-off factor. What that formula is going to look like, what that drop-off will look like when we do n as a function of time, it's going to start off at n naught, and then it's going to drop off and exponentially approach 0. Now, along the way, we have what's called a half-life. A half-life is the time at which we have half of the remaining nuclei. Half have decayed and half remain. We also, another way of keeping track of timing, we can use the half-life or we can use the lifetime. Now the lifetime we used as back when we were looking at circuits, when we were doing RC circuits and RL circuits, we had a time constant that we used, and we can also use that here, and in this application it's referred to as a lifetime. Now if you remember, one lifetime, 1 tau, is when we have dropped down to 37%. So rather than 1/2, it's 1 divided by E, where E is the natural base. So these are the formulas that tell us how the lifetime is related to the decay constant, and this formula tells us how the half-life is related to the decay constant. So once I know one of those, I can calculate the others. So you're welcome to work in terms of formulas that involve lambdas, the decay constant, or what I'm probably going to do more frequently is work in terms of lifetimes. Okay, lifetimes are also used very commonly. Now the information in Appendix F, when I look up an isotope to find out the rate at which it's decaying, that's going to be giving me the half-life. And so the half-life is what Appendix F is going to provide. So with all of those formulas, okay, now here's some better drawn graphs. This is the number of nuclei remaining as a function of time, dropping off exponentially. This is actually for carbon-14. Carbon-14 has a half-life of 5,730 years. So after one half-life, half of the carbon-14 is left. After two half-lives, 1/4 is left. After three half-lives, 1/8 is left, and then it drops off. Now, this is a related graph. This is keeping track of number. This is keeping track of the rate at which the decays are happening. This is keeping track of dn dt. So it's saying that we start off with 40 billion decays per second, and that has dropped down to 20 billion decays per second, and then 10 billion decays per second, and then 5 billion. So not only do the numbers drop off exponentially, but the rate at which the decay is happening also drops off exponentially with the same factor. And here is that formula showing how to convert back and forth between half-life and decay constants. So let's look at an example. This is carbon-14. So what is the activity of a sample of carbon-14? Now I'm going to actually use notation of capital R, where R is the number of decays per second. So they're using something called dn dt, and that seems a little complicated. So I'm going to introduce capital R, see if that's useful. Now we can calculate at any instant in time the rate at which the particles are decaying is given by the number of particles present divided by the lifetime. And this is one of the reasons I like working in terms of the lifetime. So let's look at how we would solve this problem. I would look at Appendix F. I would look up carbon-14, the 14 isotope of carbon. It would tell me that the half-life is 5,730 years. I would take that number, divide through by the natural log of 2 to get the lifetime. That's how the half-life and the lifetime are related. Now the lifetime will be longer, and the lifetime worked out to be 8,267. Now that's currently in years. I want that in seconds, because I want to calculate at what rate are the carbon-14s decaying. So I've converted the lifetime into seconds, that's 2.6 10 to the 11, using this conversion factor here. 1 year is 365.25 days times 24 hours times 60 seconds times 60 minutes, which works out to be 31.6 million seconds. That's why the years just fly by, because, 31 million seconds and the year's gone. So what happens here is, now this is a number they gave me. So if they tell me that I have a sample that contains, that's a pretty big sample of carbon-14. I'm wondering why we have that many. Anyway, that's what we're going to go with. So here's the sample of carbon-14. We have 10 to the 22 carbon-14 nuclei. And I can take that number and divide through by the lifetime that I've calculated from the half-life, and it tells me this sample will be decaying at 3.8 10 to the 10th decays per second, at least initially. It's going to decay like that for thousands and thousands of years. Now the decay rate's going to drop off. As the numbers come down, the decay rate will drop off. But these are big numbers, 10 to the 22, and then we're going to get, 38 billion of these decaying every second, and it's going to decay like this for hundreds or thousands of years. Atoms are really tiny. Okay, so that's one of the takeaways from these nuclear radioactive decay problems is, oh my gosh, there's a lot of atoms in just a little tiny speck of something. So let's calculate that. If I take 10 to the 22 atoms of carbon-14, how much mass would that be? How large is my carbon-14 sample? And for that I can use Avogadro's number, and since it's carbon-14, the molar mass that I want to use is 14 grams. So it's 14 grams per mole, because it's carbon-14, and it's only 2/10 of a gram. So I've got this sample of carbon-14, it's 2/10 of a gram. They're all radioactive. That's what caught my attention here, is I've got this sample of carbon-14, and it's purely carbon-14. Every one of those carbons is radioactive, and it's decaying eventually. But in a sample of carbon-14 that's 0.2 grams, a little tiny, piece of carbon, it's decaying 38 billion decays a second. Okay, and it's going to last for thousands and thousands and thousands of years. All right. So this is just a reminder to stop and think about this. You might think that something that has a short half-life, something that decays very rapidly, is safer than a long half-life because it's not going to be around very long. But during the time that it's around, it's going to be decaying at a higher rate. So again, to find out safety, we really have to do this kind of calculation to find out, how much of the stuff do we have and what's the rate at which it's decaying. I mean, I'm not going to be around for thousands of years to be exposed to all of this. I'm very concerned about how many decays it currently is undergoing. That 38 billion per second makes me a little nervous right now. Okay, so here's another example. This is with nitrogen 17, and then we'll check back with numbers as needed. So what it starts off with is saying I have a sample of nitrogen 13. It's 1.49 micrograms. That's a millionth of a gram, and the half-life on this is really short. So it's not thousands of years. The half-life on this is just 10 minutes, 600 seconds. So what we can do is we can start with, well, let's do a numbers calculation. It's 1.49 micrograms. That's 10 to the minus 6. This is nitrogen 13, so the molar mass would be 13 grams per mole. So every isotope to 3 significant figures, it just rounds, the molar mass just rounds to whatever the mass is. So nitrogen 13 is going to round to 13.0. I can look it up. It's kind of fun to go look up and see how close it comes into the integer value, but it's always going to turn out that way, except for hydrogen 1 is the exception. So 13 grams per mole, 6 times 10 to the 23rd per mole. That tells me that in this 1.49 microgram sample, I have 6.9 10 to the 16 nitrogens. That's the starting number. Now, when I look this up in Appendix F, it tells me that the half-life was 600 seconds. I'm converting that into a lifetime, which is 866, and I'm plugging these numbers in, and it says that at least initially, this is going to start out decaying at 8 times 10, 79.7 trillion decays per second. It's this little speck of stuff. I can't even see it. It's so small. And yet it's producing 80 trillion decays per second. Now, it's not going to be around for a long time, but even after 10 minutes is gone, it's going to still be decaying at half that rate. So it's shooting out a lot of these high-energy particles. Let's see. Here we're calculating what's going to happen in terms of the rate. What is the... here we go. It's what happens after 1 hour. So I'm now using this exponential, one of my exponential formulas, and saying that when time passes, the decay rates will drop off And I can calculate that effect by putting in amount of time, that's 1 hour later. So I'm putting in the 3,600 seconds, dividing through by the tau, and what it says is for this particular half-life, an hour later, I mean an hour later, that's like 6 half-lives have gone by. I'm down to 1.6% remaining. Well, at 1.6, I'm still getting 1.25 trillion decays per second. So I'm still getting, and that makes me a little 600. Oh, I see. Yeah, it's from 80 down to 1. Okay, good. I was just checking the numbers to see. I thought we lost a factor of 10 somewhere. Let's see. So how long is it going to be until it gets down to 1 decay per second? And it says, carrying through the calculations, leads us to 7.7 hours. So that's what the calculations look like. So practice these. Practice these. This is a really good example. Practice examples like this, starting out with a certain amount of something, and then run through, look up the half-lives, run through the decay rates, run through how many are remaining. Later on in time, how long is it going to take until the decay rate drops to something? These are good examples to practice. Okay, we've got a little time left here. I think we can still get through the rest of our items. Oh yeah, we're good. So when we look at many of the radioactive materials in nature, one of the most common alpha decay isotopes in nature is uranium-238. Now you would think in nature, why are there any radioactive materials left? I mean, the Earth has been here for billions of years. Hasn't everything that started out radioactive by now, hasn't it undergone decay? And we actually have to trace it before the formation of the Earth. So where do these radioactive isotopes come from anyway? Well, during supernova explosions, a lot of the periodic table gets generated, a lot of heavy elements get generated, and the radioactive ones get generated along with the stable isotopes. And so the uranium-238 that we have on Earth today comes from possibly supernova explosions of stars that existed in this region of the galaxy, well, more than 5 billion years ago. Now, why would the uranium still be around? Because uranium-238 has a half-life of 4.6 billion years. So it's very patient. It does not undergo decay very rapidly. Now, since there is this supply of uranium-238, and it's not going anywhere soon, this 4.5 billion year half-life, when it does decay, it alpha decays to thorium-234. So the chart is set up, once again, along the horizontal axis is atomic numbers. And so they've listed the elements, starting with element 81, 82, 83. Now where we're headed from the uranium-238 is lead. Uranium-238 eventually decays into lead. But that's a long ways away. Uranium is element 92, lead is element 82, and the masses are going to drop a lot. So uranium-238 eventually decays into lead-206. And what that involves is there's an alpha decay followed by 2 betas. So a beta decay, if you remember, beta-minus decays are actually going to move us farther into the periodic table. Beta decays happen when there's too many neutrons, beta-minus decays. So beta-minus decays take a neutron and turn it into a proton. So what happens is this. As we move from heavier elements to elements of lower mass, we end up with an excess of neutrons. So, you know, we have an alpha decay, but then we need to have a couple beta decays to kind of balance things. And then we have a series of alpha, ooh, that's a lot of alpha decays, 5 in a row. But then we need a couple more betas, and then an alpha, and a couple more betas, and an alpha. So there's like, what, 14 or 15 decays between the uranium-238. Now, nothing in between the uranium-238 and the lead, which is stable. So the lead is stable, the lead-206. In between those two, none of these intermediate isotopes of these elements have very long half-lives. That's kind of interesting. The uranium has a half-life of 4.5 billion years, but these others are 24 days, 6 hours. This is 250,000 years, 75,000. This is 3 minutes, 1.4 seconds, 138 days. So you can see the 4.5 billion years really stands out. Well, that means is as long as there's uranium-238 around, all of these other intermediates are going to be generated because when the uranium decays, it's going to go through a series of these others. Okay, so all these other isotopes are kind of waiting for the uranium-238 to decay, and then they get formed as a result. Okay, and that's what this is asking about. It's saying with these decay series, which of these isotopes is going to be decaying at the fastest rate? Well, let's think about it. Every time uranium-238 decays, how many times will a radium-226 decay? And you go, well, every time this happens once, this happens once, this happens. Oh, they all have the same numbers. So if I have a sample of uranium-238 and 1,000 of them decay, then we'll have everything else, all the intermediates created, and we'll get 1,000 decays at each one of the other steps. If we could get rid of the uranium-238, then we wouldn't have any of these other elements would disappear pretty rapidly. Okay, what about radioactive dating? Sounds dangerous. Radioactive dating, huh? Carbon-14 is an example of an organic material that we can, an isotope of an element that shows up in organic material. So carbon-14 dating, maybe you've heard about this, maybe you go online and do carbon-14 dating. Let's see. Because of high energy particles coming in through our atmosphere, there is a more or less steady rate of carbon-14 that is generated in the atmosphere. And then over thousands of years, the carbon-14 decays. We are at an equilibrium of where for every trillion carbons in the atmosphere, these are carbons that are typically part of carbon dioxide. So for every trillion carbons, 1.3 of those is carbon-14. So now we had done these numbers on carbon-14 before, the half-life. We used that to calculate the lifetime. We used that to put the lifetime in seconds. So the lifetime of carbon-14 in seconds, 2.61, 10 to the 11 seconds. What if we have a living organism that includes a kilogram of carbon? Well, where do living organisms get their carbon? And they get it from the CO2 in the air. You know, all the carbon that you're made out of, all the carbon that is included in you came from carbon in animals, and it all traces back to plants. And the plants went through photosynthetic processes. Those carbons came from the atmosphere. They came from CO2 in the atmosphere. And because of high energy particles, cosmic particles coming through, a small portion of those carbon-14s are radioactive, but that means that for every kilogram of carbon in a living organism, in an organism that's actively metabolizing, if you're taking in new sources of carbon, if you're eating food, then you're maintaining this level of radioactive carbon-14 within yourself. So, and the only way around that is to stop taking in carbon, or only eat food with carbon that has come from petroleum products or something, where the carbon-14 has all decayed, something like that. The carbon-14 that's coming, the carbon products that are coming in from plants are going to have the carbon-14 in them because they're taking it from the atmosphere. All right, let's take 1,000 grams of carbon. Now, here I am going to use the periodic table, 12 grams per mole, but that's going to tell me total carbon. So in 1,000 grams of carbon, I'm going to have a total of 5 times 10 to the 25 carbon nuclei. Now, of those 5 times 10 to the 25th carbon nuclei in every kilogram of carbon, 1 out of a trillion, 1.3, is going to be carbon-14. That says for every kilogram of carbon that you're made out of, there are 6.5 to 10 to the 13, 65 trillion radioactive carbon-14 nuclei. So don't stand too close to other people because they're radioactive. What's the rate of decay for 1 kilogram of carbon? Well, it's 6.52 times 10 to the 13 radioactive carbon-14 nuclei. That is the lifetime. Wow, for every kilogram of carbon that you're made out of, you're going to have 250 decays per second of the carbon-14. Okay, and you're probably made out of several kilograms of carbon. So your decay rate from carbon-14 is probably in the thousands. Okay, there are, I don't know, 1,000, 2,000, somewhere in that range of decays happening every second throughout you in carbon-14. Now, how serious is that? Well, we looked at the decay, and did we look at the decay energies? I don't know if we did. It turns out carbon-14, the energy that's released is not enormous, but at the same time, the carbon-14s, when they decay, they are no longer carbon. So if that carbon-14 happens to be part of your DNA, for example, well, wherever that carbon was located, those chemical bonds have just come apart. It's no longer carbon, it's nitrogen instead, and it's not going to have the same chemical properties. So anyway, something to think about with carbon-14. Here's another example, or actually it's just discussing using carbon-14 dating in materials. So carbon-14 dating works pretty well. We can actually determine how old something is. So I moved through this quickly, but here is this last example. It's an ancient bone fragment from an animal. And so we're going to take that animal bone fragment, we're going to sort out chemically, we're going to take that bone fragment, and within that bone fragment, somehow there's enough organic material left that we are able to collect 200 grams specifically of the element carbon. So we've run a bunch of chemical reactions, we've sorted out the carbon from this bone fragment. Now, if it's 200 grams of carbon, what we would expect is that if this were an actively metabolizing animal, then this fragment should contain 1.3 10 to the 13 carbon-14s. I should have written carbon-14 here to emphasize the fact. Remember the lifetime for carbon-14, 2.61 10 to the 11 seconds. So the rate at which that should be decaying, if the animal died recently, right, it was actively metabolizing right up until not so many years ago, it should be decaying at about 50 decays per second. Now what we're going to do is we're going to take that sample, we're going to put it in a detector that can actually measure decay rates, and it's only decaying at 16 per second instead of 50. How old is the bone? How long has it been since that organism was actively taking in new sources of carbon-14? And running the numbers on this formula, I just want to see how it's dropped off. So actually starting from here. So the rate now is reduced. The R naught was 50 decays per second, but the one we're measuring is only 16. We solved that equation for T, and it tells us that that organism, or that bone, is 9,400 years old. So these are very reliable techniques of figuring out how old, in this case, an organic sample is. Now what this is pointing out to us, the slide here, is that we've got a lot of different radioactive isotopes we could work from. Carbon-14 works great for living organisms because they all have carbon. And because carbon-14's half-life is like thousands and thousands of years. So that enables us to actually measure back, well, tens of thousands of years, or maybe as far as 100,000. But we can use other isotopes. Uranium-238, for example, that we mentioned, has a half-life of 4.5 billion years. We can use that in rocks. So we can actually take rocks and look and identify where crystals of uranium formed within the rock. And then we can go in and see how much uranium-238 remains and how much has been converted into lead-206. And by looking at those ratios, and we can look for intermediate materials also, we can determine at what point that crystal of uranium formed, how old is that rock. And then just to wrap things up here, this is an example of a Geiger counter that maybe you've heard of. In order to detect these high energy particles, these high energy alpha or beta or gamma particles, Geiger tubes work with all of those. We have a wire down the middle, we have a surrounding conductor. This is going to be hooked up to something of high voltage. This is saying about 1,000 volts. Now in lab, we actually have this lab right. I'm trying to remember if we're going to... So this is one of the labs that we have. I'm not sure if we're doing it this semester or not, if it got included in the list. But we do have these devices, and we can count. We can count the number of high energy particles that are being produced by some radioactive sample. Okay, so that's our first chapter on nuclear physics, which I think is really interesting. I hope you guys enjoy looking at some of this stuff. It seems like it has so many very practical, even everyday type of applications to be had. So whatever questions you guys have, let me know, stop by.